So, in my last talk, I said I would talk about chaos processes, which is the tool for establishing the restricted isometry property for partial random circulant matrices, among other things. So let me recall again. So for the partial random circulant matrix, actually the action of this matrix on a vector looks like this. So we convolve x with a random vector and then do a projection onto coordinates in omega. And this is just for normalization. So p omega is like from Rn to Rm projection onto some set omega. So this is the numbers from 1 to n. And the cardinality of omega is m. And so this was the cyclic convolution. And OK, so for xi is a random vector on Rn, and the coordinates are independent. Mean 0. Variance 1 and sub-Gaussian. So let's say the tail is bounded by e to the minus l t squared. OK, so that's the type of matrix we looked at. And now to recall, what's the RIP constant? So these were these numbers delta s. And you can write them as the supremum over a certain set Ts. So Ts are the vectors in Rn with 2 norm at most 1 and sparsity at most s of so of this quantity. So that's another way of writing the RIP constants. And now for our case, well, the first observation is if we take the expectation of Bx for this type of matrix, then we actually get the 2 norm of x squared. So, OK, that's a little computation, but I don't do the details here. So this is why we need this normalization here and the variance to be 1. So if you look at this thing, I mean, essentially we have the norm of Bx squared minus its expectation. And we need a bound for the deviation of this, or a uniform bound for the deviation from its mean. And OK, and the other trick, or well, observation is that in this case we can write, well, if we write it again, p omega psi star x. I mean, B acts linear on x, but you can view this expression if you fix x also as linear in the random vector psi. So we can write this as a matrix depending on x applied to the random vector psi. And then, so what would be helpful to proving a bound for delta S is if we can find a general bound for a quantity of that type. So we take matrices in a set of matrices. So in our case, this would be the matrices AX, where X runs through this set TS. And of A xi squared minus the expectation of okay, and the set A is just a subset of the M times N matrices. And okay, we call this thing actually a chaos process. So maybe let's specify this if so for Xi being a Rademacher, so +1 or -1 with equal probability, then if we write this out, so this thing will give the trace of A star A, and the first thing will give, we write this as an inner product of A epsilon with A epsilon, and then we get something like that. And now if we subtract the trace, well, here in the Rademacher case, if J equals L, this is just +1, so we actually get the trace. So so in this case, we will actually get a sum, this double sum where the diagonal terms are missing. And something like that is called a homogeneous chaos of order 2. And that's where the name chaos process comes from. If you have more general random variables, then, I mean, the diagonals will not, I mean, you don't get the same term here and here for the diagonal part, so you have to actually subtract that, and then you need some extra steps to estimate that, but in the Rademacher case, you get a plain expression like that. Okay, and the special thing here is that, well, a general chaos process has here some matrix. In our case, we have matrices of the form A star A, so they are always positive semi-definite. Okay. Now, I would like to present the bounds that we derived. And this is in terms of gamma functionals. Who hasn't seen gamma functionals or chaining arguments? Or who has seen that? Okay. Anyway, so let's introduce. So this is a concept that essentially goes back to Michel Talagrand. So let's assume T is a subset of a metric space. And we say okay, a sequence of subsets of the set T so TR is a subset of T is admissible if the cardinality of T0 is 1 and the cardinality of TR is less or equal to the 2 to the R So it's growing quite quickly, but okay, that's the definition. And now the gamma alpha functional of this set T, and with respect to the metric D, is an infimum. Well, in the end, overall admissible sequences. And here is a supremum over X in that set. And then we have an infinite sum. R equals 0 to infinity of 2 to the R over alpha. So this is where the alpha enters. And here is the distance of X to the set TR. Okay, so this looks a little strange if you see it the first time. So the idea is that this measures somehow the complexity of that set in that metric D. So if you look at this term, so I mean you should think of these sets as like trying to cover finer and finer this set T. So the idea is that if R increases, then I mean if you're given a point, then these distances become smaller and smaller because you're covering that set finer and finer. And so it has to decrease at a certain rate so that you can kill this 2 to the R over alpha and the whole sum is still finite. So that's basically the idea. And so the smaller this quantity is, in some sense, the smaller the set is. And the parameter alpha gives a way of some sort of fine-tuning. Okay, let me first give the next inequality. So, well, I mean, you will see that if we derive bounds, and in terms of that, it's very useful that the scales like this. In the end, because we will take a union bound and over something which scales, well, decays exponentially, well, but we will have like a 2 to the R in the exponential. So, yeah, that's basically the reason. But so there is a useful bound, which is basically, I mean, this is also what we applied in order to actually bound this quantity in the end for the particular situation that we have for this type of matrices. So this says that gamma alpha, where T can be bounded by a constant times a certain integral. So here you get the logarithm of the covering numbers of the set T and the metric D at radius U, and the whole thing to the 1 over alpha, and you integrate against U. So usually this is, I mean, this is will usually be I mean, the upper bound will be finite, because if you have a well, compact set, then at some radius you will cover the whole thing, so you just need one ball, and then the log of 1 is 0, so you don't need to continue the integral. And is everybody familiar with covering numbers? Okay, so that's the number of balls you need to cover at the number of balls with respect to the metric D and radius U in order to cover the set T. Okay. And so now we come back to processes of this type here. So bound by Talleyrand, I think it's 93 or something. You know well, it's somewhere in the 90s. So if we have a subset of the n times n matrices, and we look at the supremum of B and the set of matrices over B or J, then this can be bounded by a constant times the gamma 2 functional of that set of matrices with respect to the Frobenius norm plus a gamma 1 functional of that set of matrices with respect to the operator norm, the spectral norm. Okay, and well, okay, this works for Rademacher, but you can also use Gaussian or sub-Gaussian. That's more or less the same. So the intuition behind this is that the gamma, 2 appears always if you have something sub-Gaussian, and the 1 appears if you have something sub-exponential. So in fact, if you just consider this for a fixed B, then the tail behaves like a mixture of a sub-Gaussian and sub-exponential. So like for moderate deviations, you get a Gaussian behavior, and for large deviations, you get an exponential behavior. And this is basically how Talleyrand proved this. So he used this deviation result for this single thing here. Okay, and this is actually also what we used in this work with Joel and Justin Romberg to bound the RIP constant for this type of matrices, but we always ended up with this, well, factor s to the 3/2, so which was a little strange. So there was no, the number of sample scales like the sparsity to the 3/2 times some log factor. And it was always this component here which was responsible for that scaling. And Talleyrand himself notes that this part here is not optimal in certain cases. So there are other cases where you can really compute all the quantities involved, including this one explicitly, and you see a gap. But there was no other tool available before we came up with the next result. So this is Felix Kramer, Charles Mendelson, and myself. And okay, so we proved this in 2012, but the paper appeared this year. Okay, so well, for simplicity, we assume that the set of matrices is symmetric. That's not really necessary, but it makes the statement a little simpler, and is certainly true in this case because that set is symmetric. Okay, so the first part of the theorem states that the expected supremum over well, okay, Xi is a sub-Gaussian random vector which satisfies these assumptions here. This is bounded by a constant times the gamma 2 functional of the set of matrices A with respect to the spectral norm times the radius of that set with respect to the Frobenius norm plus, again, the gamma 2 functional with respect to the operator norm. Should I write down what this is? Or, I mean, it's, okay. So, well, the crucial improvement is here that you don't see a gamma 1 functional anymore. So you only see a gamma 2 functional, which is sort of, I mean, it's the sub-Gaussian behavior which is responsible for that. So it's actually a bit surprising because you know that the larger tails behave sub-exponentially, but still we don't see a gamma 1 functional here. And using this bound, we could then prove that in the RAP, the number of measurements needs to scale linear with the sparsity up to logarithmic terms. And so we have this bound for the expectation, but we also have a bound for the tail. No, I mean, the fact that we get a square is actually natural because, I mean, there is a square also here. So somehow, if you rescale the whole set of matrices, I mean, it should be a quadratic behavior. Yeah, okay, I mean, yeah, if you could also apply that theorem here, but then as B, you would get the matrices A star A, where A is in A, and then you would need to bound like the gamma 2 functional of B with the gamma 2 functional of A, but this is something you can do. I mean, essentially you get the Frobenius norm, the radius in Frobenius norm times this. But you don't, well, the crucial thing is that we don't have this gamma 1 functional. Yeah, so that, so we needed like a number of measurements which scales like, so at some point, I don't remember exactly, but you would get something like s to the 3½ times log something divided by m, or...
I guess my question is that really what's happening in gamma 1, or might it be that the upper bound is a loose upper bound?
Yeah, that's a loose upper bound, at least for certain cases, the one of Talleyrand. Okay, well, okay, we didn't derive a lower bound for the gamma 1 functional, strictly speaking, but as I said, like Talleyrand worked out one example where you can compute everything and you see a gap. Okay, maybe I write it. That's the soup over all A of the Frobenius norm. Well, with the risk that we forget about it. Okay, and the second part is like, okay, let's call this thing here E, which is a bound for the expectation, and so for positive t, the probability that the supremum deviates from a constant times E plus T is bounded by 2 times the exponential minus a constant C tilde. And here's the minimum of T squared over V squared and T over U. So we get a mixture of a sub-Gaussian and sub-exponential tail, and the parameters are the following. So V equals, so that's the radius in the spectral norm, times the plus the Frobenius norm of A, and the parameter U is the spectral norm, well, the radius in the spectral norm squared. Okay, some small remark. Schur-Dirksen improved this slightly and replaced V by actually V tilde being the diameter in the spectral norm times the diameter in the Frobenius norm. So basically he removed the gamma 2 out of the probability bound, which is somehow natural because you expect that this basically is responsible for the expectation, but for the tail bound you just have these diameters. Okay. Yeah, the next thing I wanted to do is to give you some ideas about the proof, at least the proof of this if we have a Rademacher vector. Okay, well, it's also non-trivial. So what we first did is have the gamma 2 bounded by this, and then bounded covering numbers. And this is similar to what is done, what was done by Rudelson Verschinen in the proof for the partial, well, for the bound for the restricted isometry constants in the partial random Fourier case. So. Yeah. I mean, it's not easy if you haven't seen it before. So basically, you need to derive 2 bounds because one of them is good for small u and the other one is good for larger u's. So you really need to do both of this. But the new thing about our result was rather this bound and not how to bound the gamma 2 functional. Okay, more questions? Okay, so let's see how far we get for the proof of A. So we first introduce a quantity NA of xi, which is the supremum of A xi in the 2 norm. So, so a quantity similar to this, but where we do not subtract the expectation. Huh? Yes, because xi is the. Okay, I state the first lemma that is crucial, and we'll deduce how to prove that theorem based on that lemma. We proved this for general things. No, sorry. Let me just state the lemma. So I will reduce to Rademacher afterwards. So let's assume psi prime is an independent copy of psi. Then for positive, for p larger or equal to 1, we have that the expectation of the supremum of a psi inner product with a psi prime is bounded by a constant times the gamma 2 functional of A and the spectral norm times the P norm of this quantity NA of psi plus the supremum over A, and here now the thing is the expectation is inside the supremum, which makes life easier. To the P over 1 over P. And okay, so I hope I will have enough time for proving that. Actually, that's a little bit more than you would need for bounding part A. For part A, you would just need P equals 1. But this is actually also the tool if you want to get the probability estimate, because what you do for that, we estimate all the moments, and then translating from that moment bound into a tail bound gives this one. Okay, so let us first see how to deduce the part A of the theorem from this lemma. Yeah, so maybe we start here. So let's do theorem A for psi equals a Rademacher. Okay, so what we have to estimate is this quantity here. Okay, and for Rademacher, this is what I just had written down. That's this double sum. Okay, and now comes a step where we introduce this independent copy. So this is called decoupling. Okay, so and here, when decoupling, we can actually also introduce the diagonal again. So here we have epsilon j, epsilon L prime, A star A Lj. So who is aware of decoupling? Okay, I fear that you have to believe me at this point. So if you have a double sum of this type, then by introducing from which you want to bound the expectation or moments or so, you can replace one of these copies by an independent copy. And, well, you pay for a constant of 4. And also by doing that, you can reintroduce the diagonal. The intuition is that here all the terms have mean 0. And here also all the terms have mean 0. If this wouldn't be an independent copy, then this would be 1 deterministically, and then you get really something else. So that's, yeah, so that's the intuition why you can actually reintroduce the diagonal. Okay, so that's a quite useful technique, because now you can condition on one variable and do expectations in the other, and this is actually what we are doing also here. Okay, so now this is actually, well, the whole thing is the inner product of A epsilon with A epsilon prime. And for such a quantity, we have an estimate by that lemma. So we can bound this by the gamma 2 functional times this. So we apply the lemma for p equals 1. Plus the supremum over A in A of the expectation of A epsilon with A epsilon prime. Okay, so let's look at this term now. So well, we bound that the first moment by the second moment. And we can also rewrite this as A, and here's A star A epsilon prime. So that's the 2 norm of an inner product. So we bound, well, actually that's equal. So we take the expectation with respect to epsilon first. Then we get A star A epsilon prime in the 2 norm. And now, yes. And now we take the expectation with respect to epsilon prime, which gives you the Frobenius norm of A star A. And, well, you can also bound this by the operator norm of A times the Frobenius norm of A. Okay, so let's now continue. So the supremum is bounded. Well, okay, now we need to take the sup over all A's. So that's the one, well, we actually need both bounds. And that's also less than df square. And okay, and now, so here we have this term here, so let's try to get an estimate of this term. And the trick is to actually re-express this in the, with respect to the original term that we actually want to estimate. So we get the expectation of that's less than yeah, and this is actually, if you look at the definition, so we plug in the expectation of a epsilon in the 2 norm. So we have okay, so this thing was actually the definition of NA up to the square. We subtract and add it again, so we get this term here. And that's actually the Frobenius norm of A squared. So, okay, and so we just derived that from here that this term is bounded by gamma 2 of A in the spectral norm plus times E epsilon plus. Okay, so actually, it's actually this term appearing twice, so once from here and once from that bound, which is this term here. So altogether, we have the square of this is bounded by this times this term again, but without the square, plus something. So from that, we can deduce that we have this here, the gamma 2 functional plus the diameter in the Frobenius norm of A. And now, okay, so we have this bound, and now we replug this bound for this term in here, and use the estimate for this term that we derived here, and then we get this estimate here. Okay, so okay, so the question is now how we can show this lemma, and this is of course where these chaining arguments enter. Well, where was the? Okay, so okay, so we take TR to be an admissible sequence, and L largest integer such that 2 to the L is less or equal to P. And we introduce the notation PR of A to be the closest matrix to A from the set TR. B minus A in the operator norm. And okay, so maybe the standard chaining argument, for those who haven't seen this yet, is to so we want to get a supremum for x, and well, okay, we can subtract this. Well, p0 is just 1 point because t0 was just one point. So, and bounding that is no problem. So, and now we want to bound the supremum of this, and the idea is to well, do this telescoping sum. And instead of bounding this directly, bounding these differences, and exploiting, well, so for these we will have like concentration inequalities, and if and we need to this then a bound to hold for all of those elements which are in a certain set TR or TR plus 1, and then we can work by union bounds. And depending on what concentration we have, we can actually bound these terms. So now we try to apply a similar idea. So assume A is in our set, and so we want to bound a quantity like that. So that's the stuff that appears here in this lemma. But what we do is we subtract pi L of A xi minus pi L A xi prime. So if we actually want to bound the pth moment, we can actually go up to level L here and still get the supremum over all elements in the level L under control in the end. Okay, and now, so the crucial step is to do a sort of telescoping sum on both sides of the inner product. And this is, so, well, I first write the actual term. So we here have PR plus 1A minus pi R of A applied to xi, and pi R plus 1A xi prime minus a similar term pi R A xi, and then pi R plus 1A minus pi R A applied to xi prime. So if you multiply this out, you see that you're only left with like the inner product of pi R plus 1A xi with pi R plus 1 A xi prime, and here the same term with pi R. So, and this is then telescoping. In some sense, this is similar to integration by part if you want. So you do, yeah, a difference, well, in both inner products. Okay, and okay, so okay, I'm sloppy at one part because you would need to argue that if you go with R equals to infinity, that you can actually approximate A as good as you want. One thing you can actually do is just to assume that this is a finite set of matrices. This would be sufficient, and then you take the supremum over all finite subsets of this, and then you still get the same bound. And okay, so and what we do next is simply to do a triangle inequality. And bound each term separately. And well, if we're done with this, this one is going the same way. Okay, so it's good to actually introduce delta R of A to be pi R A minus pi R minus 1 A. Then we will need to bound delta R plus 1 A xi in a product with pi R plus 1 A xi prime. And that's the same as inner product xi with delta R plus 1 A star pi. Okay, and now we condition on xi prime. And then this is actually inner product of a sub-Gaussian random vector with some fixed vector. And so this has a sub-Gaussian tail. So it's you can write it out as a sum, of course. And this scales then like the 2 norm of this term here. So yeah, sorry. Okay. So what we get is that probability, like with respect to xi of xi on star xi prime being larger than u times, well, L is this constant that appears in the sub-Gaussian decay. And then we have here the 2 norm of delta R plus 1 A star so this is bounded by 2 times so something like that. And now so now the thing is that I mean we need to count how many values actually this guy here can take. I mean we want to apply a union bound now, and so this can take, so delta R plus 1 is pi R plus 1 minus pi R of A, so we can count how many values this can take and this can take, so this is and this is bounded by 2 R plus 1 times 2 to the R, and you can bound this by 2 to the 2 to the R plus 2. So the probability that there exists A in A and R larger than L of, well, okay. Let me just copy this. This is bounded by the sum for R larger or equal to L, then 2 to the 2 to the R plus 2 exponential minus sorry, I wanted something else xi, and then, well, okay, let me just copy this inner. So that's the same inner product as here, but now we do u times 2 to the r over 2, and then again this 2 norm. I hope you can still read it. But the crucial thing is to enter this 2 to the r. And then we get here u squared 2 to the r, and, well, a factor L maybe. And, okay, so here we have 2 to the 2 to the r plus 2, and here we have e to the minus 2 to the r. So e is larger than 2, so actually this will kill this term, and it's also fine to sum up until infinity. So this is bounded by e to the minus constant times u squared, well, for u larger than another constant c bar. Sorry, this is getting a bit messy. So yeah, and that's basically the reason why we have this strange growth here. Okay, and now, okay, what do we have here? I'm still fine with the time, or? Okay. Sorry? Yeah, okay, I try to be almost on time. So let's look at this term, which appears here. So we can bound this by delta r plus 1 a in the spectral norm times pi r plus 1 a xi prime in the 2 norm. And yeah, so and here we can simply take the supremum over all matrices, and yeah, and this is actually this quantity n a xi prime. Okay, so we still need to reproduce the gamma 2 functional, but we are almost there. So so this means that what we have done, so with probability at least 1 minus c e to the to e to the minus c t squared, we have that this sum L okay, so this is delta r plus 1 xi pi r plus 1 xi prime is less or equal times a constant times okay, so here we had okay, let me do something like less than u. Sorry, should be t. And here we get pi r plus 1 a minus pi r a. times n a xi prime. And we can also take the supremum now here. And the supremum here. And now you can do triangle inequality, plug in A here, and then you see that this is actually basically the distance of A to the set TR by the definition of this thing, PR plus 1. So, okay, so here's, sorry, 2 to the R over 2. And, okay, whether there's R plus 1 or not, I mean, you just put an R minus 1 here, and then you get out a constant. So basically, this is less or equal than T times the gamma 2 functional of A respect to the spectral norm. And here you get this guy. And, okay, and now you need to do, basically, you need to do integration to get the pth moment of this. But this is rather straightforward. You have this decay here. And then, of course, you can plug in the other expectation over xi prime and get this term here. And, okay, so I didn't tell you how, well, and in the end, you need to do a triangle inequality here and estimate this term separately. So the supremum over all elements in the set TL. You have at most, yeah, this was T 2 to the L of them, which is essentially 2 to the P. And since you take the pth moment, and at some point you divide by 1 over P, you can replace the supremum by a sum, and you basically get out a constant. I mean, if somebody's interested, I can show this after the talk. Unless you want me to go way over time, but okay, so that's essentially the proof.